ATP is special because of its phosphoester and phosphoanhydrate bonds that are high in energy, but it's not the only thing that makes ATP special. Now, certainly these are the bonds that enable ATP to power endergonic reactions. And as we look at this table of phosphoryl group transfer potentials, we can understand that in a more intimate way. So let's just take a moment to pick out one of the most common hydrolyses of ATP is that in which ATP is hydrolyzed to form ADP and inorganic phosphate, or PI. And certainly we can look at the placement of that reaction on our phosphoryl group transfer potential and recognize that the energy generated, 30.5 kilojoules per mole, is certainly plenty to make glucose 1-phosphate. It only takes 20.9 kilojoules per mole to make that molecule from a single glucose to phosphorylate it and make it glucose 1-phosphate. That's something that ATP can power. So in order to look at just how much energy is left over after those two coupled reactions take place, let's write the half reaction for both the endergonic and the exergonic reaction that are pertinent. So we know then that in this case, ATP being hydrolyzed to form ADP and inorganic phosphate is the exergonic half reaction, negative 30.5 kilojoules per mole. Now, additionally, we need to write the endergonic half reaction. So we know that glucose can get phosphorylated to make glucose 1-phosphate. And here, because we're writing the reverse reaction of what is in our tabulated hydrolysis table, we know that if we were looking at the exergonic reaction, we'd be looking at the hydrolysis of glucose 1-phosphate. So reverse reaction here, of course, also means reverse sign on our delta G naught prime. So it would take 20.9 kilojoules per mole to generate glucose 1-phosphate. So for those two half reactions, we're essentially being able to write the net reaction of ATP phosphorylating glucose to form glucose 1-phosphate and ADP. And overarchingly, we still have a very exergonic, or at least slightly exergonic, delta G naught prime at negative 9.6 kilojoules per mole. So here we see ATP working its magic in phosphorylating glucose, or said another way, powering what would be a typically endergonic reaction using the energy of its phosphoanhydride bond. Now, I said that, this is one reason that ATP is special, and indeed it is, but the other reason that ATP is special is that it isn't at the top of this table. That is the thing that makes ATP so dang wonderful, is it is totally mediocre, which should make all of us feel better in the world. And its mediocrity is what allows it to also be made within a cellular system. So when we're eating our donuts and we're ripping and stripping high energy electrons from those and we're breaking them down, there's a multitude of ways in which we're harnessing that energy. And we harness some of that energy directly as ATP when we form high energy intermediates in the metabolic or catabolic breakdown of those donuts. So notice that one of the molecules that gets formed in the catabolic breakdown of our donuts is a very famous one called phosphoenolpyruvate, or PEP. Now, phosphoenolpyruvate is an extremely powerful molecule, far much more than is ATP. Notice that it has a delta G of hydrolysis of negative 61.9. So if we're looking at phosphoenolpyruvate getting hydrolyzed and broken down into pyruvate, hey, this is the last step of glycolysis, isn't it? Plus PI. This has a delta G naught prime of negative 61.9 kilojoule per mole. And we can see how very easily phosphoenolpyruvate can transfer a phosphoryl group onto ADP to make ATP with an awful lot of leftover energy. That is, it's a very highly exergonic reaction, even once we write the net reaction here. So positive 30.5 to make that ATP, kilojoule per mole. Wow, check that out. This is huge. So we're being able to release a whopping 31.4 kilojoule per mole in this highly exergonic phosphoryl group transfer. We'll write the net reaction there as well, so we'll be a little more simplistic here. PEP plus ADP is going to yield ATP plus pyruvate. Now, what just happened here is extremely special because ATP was generated, universal currency, right? ATP, the way that we will store energy from the breakdown of donuts. In this reaction, it was just synthesized in a process where an enzyme's substrate, in this case that substrate was phosphoenolpyruvate, that substrate is very, very high in energy, and it was used to phosphorylate ADP. So when ATP is made this way, we call it substrate-level phosphorylation. Now, really, I should have just written that in bright red. I'll just put a big red box around it because substrate-level phosphorylation, a very important term if we're going to understand all of the nuances of metabolism and to recognize the places in our catabolic pathways in which ATP is generated via substrate-level phosphorylation. So this helps us better understand ATP, but I also want to make note that you may have been scanning this table for some other interesting molecules that can make ATP. Remember talking about phosphocreatine. A quick internet search will show you just how popular creatine supplements are. The idea of taking creatine, of course, is to make a more favorable mass-action ratio towards the production of phosphocreatine to give you that really outstanding advantage in the weight room, right? So some of you may have friends who have taken creatine, or maybe in the past in your powerlifting days, you may have been taking creatine to help enhance that max power output. Phosphoarginine in lobster muscle tissues that can be utilized in those short energy bursts. You might have recognized, hey, like sort of Sesame Street style, that one of these is not like the other. Acetyl-CoA sure doesn't look like it has a high energy phosphoryl group, and it certainly doesn't. So in the case of acetyl-CoA or succinyl-CoA, as we'll meet in the TCA cycle, the bond in this that has the high energy is actually the thioester bond. This is attached to coenzyme A. So the high energy thioester is very high in energy, so there's enough energy there to power a phosphoryl group transfer, and we know that the phosphoryl group, the PI, must have to come from somewhere else in a reaction where acetyl-CoA or succinyl-CoA is the substrate. allowing for substrate-level phosphorylation. Okay, great. So this helps us understand the phosphoryl group transfer potentials just a little bit better, and it will allow us to jump into metabolism with a lot more confidence.